Hello, this is Mr. Sorrentino again, and I'm going to go over 2.1, increasing, decreasing, and piecewise functions in this Math 31 course. And we're going to start off by exploring some things on the calculator to see what's going on with this and seeing how you can find some of this information with the calculator. And then as we head into later parts of this and subsequent chapters, you're going to be doing less with the calculator and just using it more for checking your work until the final comes where you're not allowed to use it at all. Um, so we're going to get this function set up here. So I'm going to graph it. And you see I already have it entered in here. I'm also going to set my window, and let's bring this up as well. I'm going to set my window to match what's here. So I'm going to go to window, negative 10, 10, 1, that's good. Everything's good there. I'm going to let this go to negative 200, 300. I want this to go by 50s. The res, I'm not going to worry about. All these other stuff that may or may not even show up on your calculator, we're not going to worry about either. And so now I'm just going to graph it. And you get a picture that looks very similar to this, or what's also appearing in, your notes that it's already been here. So now, in the previous chapter, we did do some explorations of graphs with the calculator. They were mostly linear functions, and there were times we did look for maximums and minimums, but that's what we're going to do here. So, so finding the x-intercepts, again, where they cross the x-axis, I could use the zero function. Now, this one's going to be easy. So if I come up here to second and calculate, and I choose 0, and I want to find this one here, which looks like 1, 2, 3, 4, 5. It looks like it's at negative 6. So if I had to take a guess, I would say it's between negative 7 and negative 5. And so I'm going to let my left bound be negative 7. I'm going to let my right bound be negative 5. As you can see, there's only one place where this can intersect the x-axis in between these two. And so I don't have to really do anything for the guess. And I can see that a 0 is at x equals negative 6. This one over here, you may have some issues because typically to find a 0 using the calculate menu, you would have to have the graph go through, or you would have to have the graph have some positive y values on one side of it and negative y values on the other. So the older calculators definitely will have an issue with this. The newer calculators, I think sometimes, even though they've been programmed to try to be able to handle this, I think they still sometimes have issues with this. So let's see if that is the case. This looks like it's at 1, 2, 3, 4, 5, 6. So let's see what happens if I, go to do the same thing, calculate a 0, and let my left bound be not negative 5, just 5. And let my right bound be 7. This one doesn't have as much of an issue. Notice that it has some issue because it's been programmed. Instead of coming out to be 6 exactly, you get this 5.9999981, so forth and so on. Um, that's okay. That is basically 6. And if I want to confirm that, I could always go back, go to my variables, knowing I did have that formula in for y1, putting in the positive 6 there and seeing what I get, which is the 0. So, that's another way of confirming it. If you're using an 83 plus or an older 84, you may get an error message with that. So you may have to use something like this to test out the fact that whether or not your y value is 0 at 6. So, so far I could say for sure on this graph here, this is at negative 6, 0. This is at 6, 0. I can also use the calculator to find the minimum and maximum values, anywhere where it reaches a peak or what they call a trough. So when I look at this here, this would be a relative maximum. It's reaching a high point and then going back down. It's not the end all maximum, because I could see here that this keeps going up forever and ever, and so I probably do have some y values that are more than this highest point. Much like the same for this does bottom out and start to increase again. This is what we would call a relative minimum. It's not an absolute minimum, because I do clearly have parts of the graph that have y values that are smaller than this y value here, which looks like it's at 0. So I can find minimums and maximums in a very similar way, as long as, again, I define a small enough interval where I'm not going to confuse the calculator and have multiple possibilities in there. So much like I did before, I'm going to go to second and calculate. I'm going to choose maximum first. I'm going to choose 4 first. And I'm going to do this maximum here. So it looks like if I put it between -6 and 0, I'm going to reach that highest point I'm looking for. And so that's where I want to put it. And I notice it's at -1.999999250. So basically that means it's at -2. When you see that many nines, I mean, it's using an algorithm which kind of narrows in on it. It doesn't calculate it the way that you're going to learn how to do eventually algebraically. In some instances, not so much for cubics like this, because that's something you tend to do more in calculus, or even pre-calculus. In this course, you'll do it with quadratics and you'll get the exact values. But so -2, 256 seems to be the maximum. I'll say relative, make sure it's the relative max, not the absolute. And going back to this, I could also look for the minimum, which looks like it's happening at that 0 of 6. So to verify that, I'm just going to go to second and calculate. This time I'm going to choose minimum for 3. I'm going to go from 0. I know that's at 6, so I'll just say 7 or 8. I'll say 8. And I can see here between these two, that is the lowest point it reaches. So that's where it should end up once I hit enter without having to place it there. So I get 6 repeating zeros and then a 1, 1. That's, again, due to calculation errors of using an algorithm and search pattern. So that is 6. So going back to here, this is also the relative min. So the calculator can be used to find these pieces. Now the thing is, you're asked a question now. Okay, with this information, how can I describe where this function is increasing and decreasing? And you're asked to do that right here. So based on the information we have, knowing now where the zeros are, knowing where the maximum and minimum are, how would you describe this? And typically we do this in interval notation. So let's put a little star here. See if you can give me this in interval notation. Well, for increasing, now when I judge this and I follow the graph, I'm going from left to right. So I'm always moving left to right. And so if I follow along with the graph up here, maybe make this a little thicker, I can see I start off increasing, 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 increasing until I reach a maximum. When I reach that maximum, I'm not doing either. I'm not increasing or decreasing. I'm actually just turning around. Then it decreases and then, hits this bottom out point, and then I start increasing, increasing, increasing again forever. So the interval for increasing I would say goes from negative infinity to the x value of negative 2. And then now it's not going to be, it's not increasing at negative 2 because at that point, that maximum point, it's turning. It's neither increasing or decreasing. It's basically stopped. It starts increasing again after 6. So that interval would describe where f of x is increasing. Whereas for decreasing, I can see that it's decreasing between these two values. That's the only place. It's increasing anywhere else. Again, as I'm moving from left to right. And again, I'm looking at the x values. So I would say that it's decreasing for values between negative 2 and positive 6, not including those values. And so those are your intervals of increase and decrease. We'll talk more about those and minimums and maximums as we move along to other parts of this course. Let's look at example 1 now. Now here you're given this function y equals f of x, and you're asked to describe where f of x is increasing, decreasing, and constant. So notice it is a finite graph. This graph has points, endpoints here and here. And I can see that. It doesn't go on forever and ever. At those points, when I'm starting off, it's not doing either. It's after, x equals negative 7, it's increasing. And then it, reaches a highest point. It looks like at negative, when x is negative 4, decreases where x equals negative 2. That's where it reaches that point there. Levels off and stays at the same height from x values of negative 2 to 3. So that's where it would be constant. And then it starts decreasing again from 3 to 6. And at 6, it's ending. So it's no longer decreasing at the point I stopped. So for increasing, again, I'm going to kind of follow along. Let's do that. This color here. So I can see that I'm increasing as I follow from left to right, going in this direction. So, and that's the only place it's moving upward as I move from left to right. And I can see here that I have a maximum here at negative 4, 6. So it's the x value I'm looking at here. So it's increasing when I go from negative 7 to negative 4. So on that interval, I'm increasing. Decreasing, I'm decreasing here as well as here. At this point, I kind of turned direction and went constant. Same thing here. I turned from going constant back to decreasing. So I'm not going to include those values, but it's important to know what these points are. It's negative 2, 2, and 3, 2. So going from negative 4 down to negative 2, I'm increasing. Going from 3 to 6, I am also, or I should say decreasing. And same thing from 3 to 6. So I'm decreasing for x values going from negative 4 to negative 2, not including these because the negative 4 and the negative 2 are actually turning points. And then I'm going to do so again when I start up at 3. And I end up at x value of 6, because this is 6, comma, negative 4. And again, I'm focusing on the x values. I'm focusing on the x values that are creating these. And of course, the constant part is happening right here. And that's happening between x values of -2 and +3. So -2 to +3. When I do intervals of increasing, decreasing, or constants, I'm never going to have brackets being used. The reason being is that the endpoints of increasing and decreasing are going to be at maxes or mins, or possible turning points if it happens to go constant for a while. Um, if it's a finite graph, it's starting at a particular point, but at that point, at the starting point, it's not doing anything until you start moving beyond that point. If it's an infinite graph, then well, you can't reach a number, so you're going to have infinity, so there'd be no brackets. So intervals of increase, decrease, and constant for a graph, I should never see any brackets being used for it. Now let's look at some applications of minimum and maximum. So a very famous problem that gets used, and you're going to be able to do this only by using a calculator. And problems like this, they're more or less expecting you to set up the problem. That's more of what they want you to be able to do than necessarily finding the actual maximum. There's ways you could do that, but that would require you to use calculus. You have a box that you're going to make out of an 8 by 12 inch piece of paper, and you're going to cut off corners. So basically, what you're seeing here is, these corners here, 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 and here are eventually going to be cut off. And, this, and this are going to be folding up to make the box. This, of course, is going to be the bottom of that box. They want you to know how to cut this paper in order to get the maximum possible volume. So there's two things I have to do. I know the volume is length times width times height, but I got to get this to be in terms of one variable only. Otherwise, I'm not going to be able to graph it. My calculator is only able to handle graphing one variable things, at least in the modes that you're going to keep it in. The second thing is I'm going to need to figure out a domain, because there's going to be a limit, to what I can cut off. And I'm going to call these, these squares having x by x values. So these squares are all going to be the same size. They're going to be squares, so the two sides all four sides are the same, and I'm just going to call them x. So I need to figure out the domain of x along the way, because when I deal with volume, volume is a cubic function, and cubic functions can turn in a couple different places. And I want to make sure that I'm looking at the right portion of the graph to get the maximum I'm looking for. And the domain helps me establish that in part. So the first thing I'd have to do, though, is I got to get this in terms of one variable. So when I look at this diagram here and think about it getting folded up, the height is the x value, because that's what's coming from these x's here. When I cut these away and fold them up, that's going to be the height of the box. So h is going to equal x. The width, which is going to be this part right here, going from here to here, that's the width. How am I going to put this in terms of x? Well, it's starting at 8 inches, and I'm subtracting away 2x's worth. Because, this is x here, this is x here. X, w, and another x add up to 8. Therefore, the width has to be 8 minus 2x. In a very similar way, this being the length of the box, x, L, and x together should have to be 12, which means L is going to be 12 minus 2x. Now I have all three of these in terms of x, so now when I write a volume formula, I'm going to have The length, which is 12 minus 2x. The width, which is 8 minus 2x, times the height, which is x. Now, I could multiply that all through, go through the process of distributing and foiling, which are things we will talk about as we move through the course. We haven't reviewed it per se yet, but it should be something you still remember. With all honesty, I really don't need it at this point because I mean, the only way for me to find the true maximum is for me to graph it and probably using the calculator to assist me. So this is a good enough function, but before I figure out, like, put this in and graph it, I want to figure out, well, what are my limitations here? Because there's only so much I can cut away from x. Well, if I look at, this side here, this is the shorter side of the piece of paper. The most I can cut off, the most x can be, is 4. Because if I cut off 4, and actually that's going to be too much because I would take away the entire 8 inches of this width. So, so there would be really like no width at all in that kind of scenario. So I know that x has to be less than 4. If x is equal to 4, then I'm not going to have a width of the blocks. If it's more than 4, then I would have a negative width, which doesn't make any sense. So I'm looking for x values that are less than 4, but I also know that the x value has to be more than 0 because unless I cut something, I'm not going to have anything to fold this box and fold into this box. So x has to be between 0 and 4, so that's my domain. That makes this a little useful as I go through now to use my calculator, because pulling my calculator up, I have my function. Let's just, let's see if I could. Yeah, that works. I'm going to graph my function now. Clear this. And again, I could FOIL this out if I want to. I chose not to because it doesn't really matter for this. It is going to be cubic. If I graph it from the previous one, I may not see anything. Well, I'm getting enough there. But notice it does have, it goes up, then down, and up. I'm assuming I want this maximum here, and it makes sense if I think about it. Let's let my window here reflect this a little bit. My max here is going up to 300. Maybe just make that, I'll make this go down to negative 50. Focus more on the upper part. We'll say 200 on this, going by 50s. The x values, just so I can see the axis, I'm going to say this is negative 1. But I'm going to go only up to 5. Because after that, I really don't matter because x shouldn't go beyond 4. As a matter of fact, even to make it more so, let's stop it at 4. And if I graph it now, it's only this part of the graph I'm concerned with, which it clearly does have a maximum. I want to find out where this maximum is, and I'm going to figure out what the x value is. So I'm going to now go to my calc menu, hit maximum. It's going to ask for a left bound. I could see that I have 1, 2, 3, and 4 here. I could say, okay, well, I know it's between 1. I know it's between 1 and 4. So like one place it reaches a maximum. So the maximum occurs when x equals about 1.57. They're asking for the maximum volume. So I already have that answer. I'm looking for what the maximum volume is. Now, sometimes they might ask for the dimensions. They might ask for how much do you need to cut off. X is how much you would need to cut off or what the new height is. go back and answer the question. Now the thing is, you have to remember that this function I drew on my calculator is the volume in terms of x. So my ordered pairs that I'm generating from that are x coordinates, which is how much I'm cutting off from the box, and the volume of the resulting box. So if I come back to what I got for my maximum was 67.6 blah blah blah. That is the maximum volume. So the maximum volume, I'm going to say, is 67.6. And that's going to be in cubic inches. And I'll maybe put a wavy equal sign here so to say it indicates approximately. And so that's the maximum volume. So I answered the question that's in front of me. Again, variations, they might ask for what are the dimensions of the box that would maximize the volume. How much would you need to cut away from the corners to maximize the volume? There's different ways they can ask a lot of the same question, but you have to, make sure you're answering with the right piece of this to do it. And with the calculator, it does make it a lot easier, but once you learn how to do it with calculus, it's not much harder. Just there's certain rules you have to learn by calculus to do it. Now we get into some piecewise functions. A piecewise function is pretty much what it says. It's a function made up of pieces of other functions. And so the pieces here are part of x squared, 5, and negative x plus 9. So there's actually three functions here: y equals x squared, y equals 5, and y equals negative x plus 9. The issue that people have with drawing piecewise functions is that they don't think about what's going on, and they end up creating gaps that go on with this. When I look at the domain, and I'm going to show this here, the domain for the function, because it's defining what goes on for x less than or equal to 2. So x being less than or equal to 2 means I have this part of my number line being represented with all these x's. So any x so far comes from here. Well, those would go into the x squared. 2 is not going to be, but the thing is, here's where 4 is. 4 is included. Anything between 2 and 4, which means, anything that gets closer and closer to 2 is included. So people want to make the mistake and say, well, I'm going to start this at 3, and they leave this gap here. Because they say, well, a number that's more than 2 is 3. Well, so is, 2.1. So is 2.01. So is 2.0001. So forth and so on. So they sometimes don't account for that and end up putting gaps into a piecewise function that really shouldn't be there. And then from 4 and beyond, so basically the domain for this function that we're being given here is all real numbers. And so we have to remember that, so although this function here, the number 4 would not be plugged into negative x plus 9 per se, 4.1 would be, 4.01 would be, 4.000001 would be, and those are getting really, really close to 4. So when you graph a piecewise function, what often you're going to see in there is something we've indicated on number lines already, and that's using open circles versus closed circles. So let's have a look at this. Notice how I have this set up. I have some values that are less than or equal to 2. So I basically have, this part here is going to get plugged into, f of x equals x squared. This part here is going to get plugged into f of x equals 5. Notice that the 2 has been repeated here. That's because even though 2 technically is not included in this, values getting infinitely close to it are. And the same rationale for this, these are going to get plugged into f of x equals negative x plus 9. So as I go through this, I have to be aware of these and make sure I'm adjusting accordingly. So when I plug -4 into x squared, I get 16. Here I'm going to get 4. Here I'm going to get 0. Here I'm going to get 16. Now, even though I'm only choosing these four x values, any values in between them are going to follow the pattern I see there. And this should be 4 again, not 16. Oh, what's going on there? Negative 2 squared is 4. So I'm going to plot these points. -4, 16, -2, 4, 0, 0, +2, 4. Now, it was included on this line here, so I'd put a closed dot here. And there's that parabola we've been talking about, which we're going to study in more detail as we move through this course. Especially when we start talking about quadratics and we actually find maximums and minimums of those types of functions. So I have that. When I do f of x equals 5 and I plug into 2, theoretically, I mean, if x is 2, this is 5. If it's 3, y is 5. If it's 4, y is 5. This would be an open circle. So when I do this, I say, okay, well, at 2, 5, I'm going to put, let me make this a little thicker, an open circle, because, you know, this is getting infinitely close to this point, but it's not really this point. At 4, it can't equal 5, so there's a closed dot there. And I have this part. Notice that there's a gap here. There's a break here, which, you know, piecewise functions will sometimes have. Now I go to the last line, 4. If I plug 4, and go to a different color, plug 4 into this, I get 5 again. I plug 5 into this, I get 4. I plug 6 in for x, I get 3. This goes on beyond 4 and forever. So technically I would put a open dot here, but since it's already been closed before, I'm going to leave it alone. So 4, 5 is a point. 5, 4 is a point. 6, 3 is a point. And it follows this pattern forever and ever. And it follows this pattern forever and ever in that direction. So that is what this piecewise function would look like. Notice that there are no gaps in x values. There might be some gaps in between y values, and that's to be expected, but in the x values I shouldn't see any. So that's why oftentimes you should repeat values where the breaks are occurring. Just make sure you know where the circle gets filled in and where it doesn't get filled in, so you can represent holes and whatnot. So that's the example 3. And you do see like a little calculator snippet on there, which I'm not going to go over in this one. You know, how you can put it in your calculator. Just to show you really briefly the inequality signs, just so I can show you where you can get those from. If you pull out your calculator and you go just above the math button, it says test. If you hit second and test, that's where you're going to find your inequality signs. So, you know, if you just graph it, making it look like this syntax here using the parentheses, it's going to graph a piecewise function. The only thing is you're not going to see, as you see here, you're not going to see, I mean, you can kind of see the gap right here. Get the pen. You can see the gap right here. I'm not going to see the open versus closed circles, because the open circle, we're indicating a hole, but holes are infinitely small in math. And being infinitely small means you're not going to be able to see it. So the calculator is not going to show any kind of symbol that identifies it, but you can see how it has that small break here and how it's more continuous for here. But that's basically the same graph we just got done doing. Let's look at one more piecewise function. Now, one of the ones that they do demonstrate in the book is the absolute value function. And I would say clearly look over that, because the absolute value function is a piecewise function. Piecewise functions Um, Kind of getting back to it, are functions that tend to have breaks, sudden sharp corners. Those are some even some gaps. Those are indicators that you have a piecewise function. An absolute value function, what they kind of tell you about, and kind of summarizing it, but go look into it a little bit more detail. If you graph an absolute value function, it tends to look like a V shape. And again, since it does have that sharp corner to it, that indicates it is a piecewise function because it's obeying two different laws for different x values. For certain x values, it's just repeating the x value. For other x values, it's doing the opposite. So it is a piecewise function. But the other piecewise function that they want you to have a look at is called the greatest integer function. They do throw this at you a couple of times, so I do want to explain what it is so that you are familiar enough with it to know what they're talking about and how to use it. Um, the greatest integer function, your textbook uses this notation right here with this, the brackets that have like a double bar on it. Some books will just use a regular bracket around it. So always make sure you're aware of that fact. As a matter of fact, I think your calculator could do the greatest integer function. It doesn't use a bracket. It actually does have an integer function. Um, but basically, another name for the greatest integer function is the rounding down function, which means if it's an integer, it leaves it alone. So for each one of these instances here, -2, -1, 0, and 1, it's not going to do anything because it rounds down to the nearest integer. Now when it says round down, it means it's going down in value to the nearest integer. So if I'm at -1.99, if I round down to the nearest integer, that's going to be -2. Because -2 is less than that. Same thing with -1.5. Same thing with -1.1. And so if I graph all these at -2, I'm going to be at -2. These are going by ones here, so as I get closer and closer to -1, nothing happens. Notice how I get infinitely close. I mean, I can get really, really, really close. I got -1.1 here. I could go -1.0001. It's still going to be -2. So it's going to still follow here until I actually reach -1. At -1, I'm now going to be at 1. At -0.999, it's going to round down to -1. At -0.5, it's going to go down towards the nearest integer. So that's going to be -1. Same thing here. Same thing here. And that's why, you're going to see the same kind of thing here. As I get closer and closer to an x value of 0, if I'm going from -1, this is going to stay at -1 until I actually reach 0, where I'm going to have 0 as the answer. Now, if I go beyond that, this is going to round down again. So at 0.001, I'm going to go down to the nearest integer. So that's going to be 0, 0, 0. Even if I'm getting really close to 1, I'm not rounding off, I'm rounding down. I'm going down to the nearest integer. That's still going to be 0. Until, as I get closer and closer to 1, it's going to stay there until I actually reach 1. Then I'm here. And this continues on forever and ever. They also have rounding up functions. I think this one actually does bring it up at some point in the book, so be on the lookout for an explanation regarding that, but it works kind of the opposite. And it's going to round up to the nearest, integer value, but that's what this graph looks like. And that's why they call these a step function. You can see it kind of has like a step pattern to it. So it's called a step function. You're also shown that how the calculator can be used to do this. Again, you're not going to see the open dots versus the closed dots because remember, these points are infinitely small, so your calculator is not going to be able to represent them, of course, and it's not programmed to put open dots there. So, but that is the end of what you had to do in 2-1. So if you have any additional questions, please make sure to reach out. Until I see you in class and next time, have a good day.